So this is something that you guys should be comfortable with, but for those of you that, for whatever reason, didn't study this in pre-calc, so it says find all points where f prime of x equals 0 for the intervals from 0 to 2 pi. So we know that f prime of x is equal to the derivative of cosine and negative sine x. Okay. So find all points where this equals 0. Okay. This is where it's good to know a general idea what a graph of sine and therefore negative sine looks like.
Okay.
So if we go.
Oh, it's like this. Cosine is the one that. Cosine goes. No, sine goes like this. One of them starts in the middle and goes down, right? It's not like this. Right. It goes.
So sine. Let's do sine in a different color. Let's go with sine brown. So sine. Here, and the period that just sine has is just 2 pi. So you start at 0, starts at 0.
That's the opposite, right? So it's 0 at 0. Move down.
Yeah, it's 0 at 0, and then up to 2 pi. So let's go ahead and graph the blue. So then, yeah, so negative sine to reflect in the x-axis. So imagine you're just doing the mirror image of it. As best you can.
I think you're the first math teacher I have that can draw graphs well.
Really?
Yeah.
Thank you. Alright, so we know that a full period, this is the thing that I guess you guys should have tried to, one of the things you should retain, but if it's not, that's okay. So sine, cosine, and their reciprocals have a period of 2 pi. Okay. Tangent and cotangent are the ones that have a period of just 1 pi. So period is where, and this is just the stand. This is just the parent functions, right? Where before it repeats, the distance at any point of the graph before it repeats the exact same pattern. So up and then down, and then if I continued on, it would do the same thing over and over. So these are the waves here, right? And the reciprocals would have the same period of 2 pi. So where does this equal 0 on the interval 0 to 2 pi? So start just going from 0 to 2 pi and including those endpoints because it's closed interval, including the points 0 and 2 pi. So looks like it's 0, pi, and 2 pi.
I thought it was coordinates. Does that work as by points?
Yeah.
I did 0, 0, pi.
Yeah, that's fine.
Over 2 pi up, nothing. Oh, 0 half, 0, 5. So those are all the points that sine x would have to be for sine of x to be 0, negative sine of x to be 0.
Yes. Yeah, from just this interval. Now, of course, there's an infinite number for the entire domain.
Yeah, yeah.
Because it keeps going on forever and ever. So they need to specify. Now, if they didn't specify, you could write a simple formula, x equals 0 plus or minus k pi. That would cover everything. Like just for this interval, specifically 0, pi, and 2 pi.
When I'm talking 2 pi and sine, I just think put 1, which is why I didn't put line.
Okay. So the reason it's giving you 0.1 is probably because your calculator is in degree mode and not radian mode. So that's I'm glad you said that because that's one thing that I remember when I was using this calculator. You would do work and you're like, what did you forget? Oh yeah, it has to be in radians. So make sure whatever you're dealing with is in the right mode. It can be easy to forget radians or degrees. Mostly you'll be dealing with radians, but in case you have a problem that deals with degrees, make sure you're in degrees. Okay, so today I want to kind of just review the last session because I feel like the notes were not very clear on the board, so I went and cleaned them up, and we're going to actually go over some more examples together of how to find extrema analytically. Finding them graphically is very simple. You just graph and you can see, oh, okay, within this window, there's a max here, there's a min here, right? But if you just needed to do it analytically, that's what we're going to focus on. So, let's start off with just this basic example here. So you have some graph n of x. And if I just want to say on the interval from b to f inclusive, there is an absolute max at x equals c and an absolute minimum at x equals f. You all agree from b to f, you can see, okay, this is definitely the maximum value and the minimum value would actually be at f for that interval. So give it to you graphically, again, very quick and easy to see. In fact, let me go ahead. Let me actually put the extreme value theorem right here at the bottom of the perfect place to put it. And this is one of those theorems that I think a lot of you said that, oh, that seems kind of obvious. But it's one of those things like the difference of squares, being able to recognize, oh yeah, well that theorem tells me that there has to be both a maximum and minimum value if this is true. And so it says this. Extreme value theorem. This is particularly a good thing when you have the part of the AP exam where you have to give free response answers. It's good to know this. And it just says, if, say, f is continuous, on a closed interval, then f has both a maximum and minimum value.
Now, would we call F and C absolute?
On the interval. Just one second. Sorry, what was the question?
Could we call C and F absolute extrema, or would they be considered local because they're within a...
Both. Good question. All absolute extrema are local extrema.
I thought it was the other way around.
What's that?
I thought local extrema were the ones within the interval.
Local extrema, so again, all absolute extrema are local extrema. It depends on the interval that you're specifying. So for example, if I said from the interval from B to, sorry, let's say from E to H. From E to H. At x equals h, you would have an absolute maximum, and at x equals f, you would have an absolute minimum. So again, so we're talking about just that neighborhood, you can actually refer to it as
I thought
absolute.
that was local.
Yeah, again, all absolute extrema are local. They actually mention this very thing here. I know this is where it gets confusing. I don't want you to focus too much on it, but do understand that all absolute are local. So, for example, on page 189, it says an absolute extremum is also a local extremum because being an extreme value overall makes it an extreme value in its immediate neighborhood. Okay, don't stress too much about it. Now, if we were talking about the entire domain, not some closed interval, the absolute maximum does not exist because this guy continues to increase. Nor is there an absolute minimum. But there are local extrema at x equals f, there's a local min, and at x equals c, there's a local max. But you would call them absolute if you're specifying an interval like this. So this is absolutely correct. We would call it an absolute max and an absolute min. Don't worry too much. Global is another one too. If you hear the word global, absolute, they're synonymous. Sorry, this is blocking the word right there. So if f is continuous on a closed interval, AB, then f has both a maximum and minimum value on the interval. So all it has to be is continuous on a closed interval, and you're guaranteed a maximum then. Okay. Again, sounds very simple, but again, it's one of those things where it's like, in order to express your ideas mathematically on the AP exam, you'd be very comfortable with this.
How do we solve that graphically? Or not graphically, analytically?
All right, we'll look at some of those. So, of course, I think we all agree, given it graphically, it's very easy and quick to see. Okay, so now we'll go on to analytically, this is the more rigorous aspect of it. Okay, so first off, let's understand what a critical point is, and then this will be part of how to find all of the extrema. So first off, a critical point is a point at which f prime equals 0 or f prime does not exist. And moving forward, I'll just use D and E for does not exist. Okay, so critical points. One more time. Critical point where f prime equals 0 or f prime doesn't exist. So here's how to find extrema. This is it. Number 1 and 2 are the critical points. 1 where f prime equals 0, 2 where f prime does not exist, and last mean point values, and that's it. And this will allow you to find extrema for any interval.
I still don't understand. Before we had talked about how do these relate to extrema.
Mm-hmm.
So by
What critical
checking
points?
These, yeah. Well, no, these 3 things that you check.
Yeah.
How do those?
Oh,
things find
just to
extrema?
grasp it. Like,
Yeah,
how do I know this
how
covers
does
that?
it connect?
How does it cover everything, and
Yeah,
how does it
and
connect?
How does it even connect?
Okay, so let's look at now this example here where we started off. Good question. So here, there's no issue where f prime does not exist. Right? There's no like asymptote. There's no cusp or corner. Okay, so for this one, you would agree that where there's a change in direction, there could be possibly, at least, if not the extreme, definitely a local. But we'll figure out which one is the extreme. Let's say if there were several, that's why you end up comparing all of them. But you're going to list all of them, and then you just compare, right? So for example, let's say you didn't see this, but you saw just the function.
More extreme than the other because
Just the y value, whatever the y value is.
Oh, okay. I was like, because the curve, they both equal 0. Like I thought you were talking about when it curves.
Yeah, okay, yeah, how to find it. But then, okay, so let's say you know that there is a local extrema at x equals c. But you don't have this, but you just know it's there, okay? Then you actually plug in c for x into the original function and evaluate the function for c. Okay, now I know the value of that function at that. And let's say then there's nothing else going on in terms of where it doesn't equal 0, or sorry, where it equals 0 or it doesn't exist. So then the endpoints. So then you find n of b and n of f, and then you just compare those 3. You're going to have a max and a min according to the theorem.
Okay.
And when you compare the 3, you'll see which ones they are. I actually have an example where basically what I'm saying is broken down. So good question. And now the other part where it doesn't exist. So think about if something funky was happening in between here. So let's go ahead. Let's say you had, let's do quick. So let's say you had something going on. This goes up, and down here, and then breaks off here. And then say goes down forever, and this also goes down forever. But you don't have it graphically, but analytically what's going to happen is when you set f prime equal to 0, you're going to find this guy, and you're going to find this guy. And then when you find out f prime does not exist, it's going to be here.
Okay.
Yeah.
And then you have to also do the endpoints if you needed an interval.
Yep, exactly.
And then you have to take all 5 of those points and figure out which one has the greatest y value.
Yep, the greatest value of the function, exactly. That would be your
And that's
local
your-
or absolute, because you're talking about within a closed interval, so you can call your absolute max.
Okay.
And then the one that's the absolute lowest, the absolute minimum.
Okay.
Exactly.
That makes sense.
Yep.
So okay, yeah. All right.
Yeah. Now, if you wanted to know for the entire function with no intervals, then you would have to know the in behavior. You have to know, what's happening as x approaches negative infinity and what's happening as x approaches infinity, because then you would find out, oh, because I know my in behavior, this guy goes down forever and down forever this way. I know that this is an absolute max over the entire domain.
But your absolute min is.
But there would be no absolute min.
Yeah.
Because you know that, okay, this is going to negative infinity, and then this doesn't compare. Exactly. So good. So we want to be comfortable with both finding local or absolute extrema over the entire domain as well as interval. So again, how to find extrema, where f prime equals 0, where f prime does not exist. So this is going to give you turning points. This is going to give you local mins and maxes. This also will give you local min and max. But this is going to be where it's a cusp or a sharp or a corner where f prime does not exist. And then endpoint values, of course. You need to test those. Yes?
What would be an example where you have more than one point where it doesn't exist?
Example would be, let's say you get something that's in factored form, and you know, okay, we can't have division by 0. That's the issue. Anything, any value of x that would give you division by 0, that's where, okay, that's where I have an issue. That's where I have that does not exist. Fine. Okay. So this is example page 190. I went ahead and we did this one before, but I went ahead and cleaned it up a little bit. We'll just go over it again. Where f of x is equal to x to the 2/3. Now, if you look at this, x could be anything for the function f. Okay, but what you're really testing, what you need to do is, okay, f prime of x, where that equals 0, where it does not exist. So you go ahead and do that, and what I do is write all of your negative exponents and positive, arrange them necessary, however necessary. So if you look at this, okay, there's no value where f prime of x could equal 0. So we take care of that. That was like step 1, okay?
So what does that tell you? That there is, like, that doesn't give you.
There's nothing to consider for that part. So then you go to the next part.
Okay.
Yeah, okay, so now where's undefined? Oh, I know where it's undefined. When I have division by 0, well, what would make this 0 when x is 0? So I know that that is a critical point, where f prime of 0 is undefined, and that is when x is 0. So I should not have, I don't know how that happened. That happened just now, yeah. So 0, 0 is a critical point.
Okay. What does that tell you about the extrema?
Well, that could be one, but then the last thing we have to test, and let's continue on the next slide, are the endpoints. And they specify this interval, example 3 on page 190, they specify the interval -2 to 3. Yes? Yeah, sure, go ahead. And so now let's actually do -2 and 3. So f of -2 gives you a value of the function of q root of 4. F of 3 gives you a value of the function of q root of 9. So you're comparing this one, and 0, 0. Exactly.
And so,
If we look at just the y, the value of the function, 0 versus q root of 4 versus q root of 9. Of all three of those, q root of 9 is the largest. So we say there is an absolute max value of q root of 9 at x equals 3, or when x equals 3. And then an absolute minimum, well, the smallest of all those values is 0, and that occurs when x equals 0. And that's all you do. So critical points and endpoints. And so we have checked all the critical values and the endpoints. We are done. I was thinking that I would just assign homework and we start homework together, and you guys can finish wherever we leave off, or we go and touch on the mean value theorem. But we could save that for another lesson. So homework. Or if there's any guesses, so find extreme values of examples. Go ahead, write down the homework.
Never mind.
Why did they have you on?
Yeah, but I can't say. She can get away with whatever she wants, but she has all the
1 through 9 will be pretty quick.
suggested homework. Does that mean it's mandatory? I don't think so. Suggested and suggested.
And then use analytic methods to find the extreme values of the function on the interval and where they occur on numbers 11 through 18, which is the same directions for 19 through 30. I want to see how difficult these are. So it looks like they have some kind of a funky ones for 11 through 18, but you should be comfortable with natural log and sine and so forth.
I think maybe if this is the first time. I think it was really good.
Oh wait, what page is this?
This is page 194.
Wait.
Yeah, because your leg is so bent.
We could just stop there. That's enough homework.
Yeah.
Okay, so I mean, this is just suggested, so you don't have to do all of it. I would definitely do enough to where it's like, okay, I feel solid on this. I feel good on this.
This was fun. Homework was great. I'm comfortable with everything, so I'm not going to do it.
Number 1 through 9, you're just looking at the graphs. So we could probably look at those together on page 193.
Everybody books.
Number 1,
So how do you do minimums when they both the intervals have ends at the same point? Would you say at x equals -2 and x equals 2?
yeah, minima. Good question. So when they have the exact same, so minima at -2 and 2, and a max at 0. And the actual values, of course, for the minima is 0 and the maximum value of 2. So that's pretty straightforward.
You
1.
wrote it like.
Okay, there is still one.
So y prime would be equal to 4x minus 8. So where is this equal to 0? So we set it equal to 0. And so, yeah, so add 8 divided by 4, so at x equals 2.
Do you have to find the y value for that?
Does it ask for the, yeah, it asks for the extreme values, so you definitely have to find what the value is of that function at x equals 2. So at x equals 2, we have the point 2. Plugging it back in, you have what? 4 times 2 is 8.
So it's 8 minus 16.
8 minus 16, which is -8, plus 9 is 1. So that's one of them. The value of it being 1.
Now would there only be one because it's a parabola?
Yeah, so again, for a parabola, what you just found is the vertex.
Ah.
We could have done that for.
Wow.
Yeah.
Oh, it would
Yeah.
have been so much easier than doing with.
But what was it? The p over
2 minus 8 or
Right. So this is one of those instances where calculus can make things a lot easier with finding like any sort of turning point, change in direction.
You didn't know calculus.
All right, so the in behavior we know, so there's nothing else to really test. There's nowhere where this is undefined, right? There's no division by zero possibility. No division by zero possibility, so we've covered everything. This is the only extreme value, and we would call it the global or absolute minimum of the function.
This is one way of doing it. It looks like it's like coming around. And it's literally just like what's going on. The other way of doing it is like,
Throwing that across the room.
All right, so make sure you guys are comfortable if you have to deal with something like number 11, f of x equals 1 over x plus ln of x. Number 11, you'd be comfortable with all the suggested homework. So number 11, you have, it's not polynomial. It's not polynomial. Did I not write that? No? Oh, sorry.
It's the same thing we've done for everything else. You just said you can find the
Thank you for letting me know.
sorry.
Don't view homework as something that there's to work against. It's something to help you prepare for a quiz or a test. I know you guys know that.
I love the word suggested. I've never had a teacher do that before.
So number 11. So number 11, you have to be comfortable with that. Yeah. So let's look at number 11.
I think I did
We
it.
can finish with that.
Oh no, I didn't.
Oh yeah, that doesn't look like one at all.
So number 11 says f of x is equal to 1 over x plus the ln of x, natural log of x.
Why?
And we're going only from 0.5 to 4. Which actually makes it more convenient. If you weren't familiar with this, and off the top of my head, I have no idea what this looks like off the top of my head, but because they give me endpoints, oh great, then I don't have to worry about end behavior, right? I'm just, okay, f prime equals 0, f prime doesn't exist, and then endpoints.
How do we know end behavior without a graph?
Good question. They expect you to only know certain ones. Like for this one, I can tell you the fact that they're giving you the intervals.
But
For all of these, they don't.
Like you would know
Okay, the only way you really know is with a graphing calculator. A graphing calculator, so definitely you can see it.
True.
Or a table of values, but then again, you may not see exactly what's going on. So f prime of x would be equal to, if you imagine this is x to the negative 1, negative x to the negative 2, plus 1 over x, which is equal to negative 1 over x squared plus 1 over x. Yeah, so is there any values where we can have this equal to 0? And I'll give you a hint. There's a max value, a minimum value, and a local max.
Why would there be all three? Because you have an interval, so I thought they were all.
Well, okay, well, there's remember, like when you do all three, to find the absolute, there's only going to be an absolute max and an absolute min.
Yeah,
But you can say they're all local. All three are local.
So there's gonna be unknowns, obviously, and there's gonna be,
Right,
so it does not exist.
X can equal
X
0.
can equal 0, but that's where it doesn't exist, right?
Yeah.
Is that correct?
So think about if we let this be 0. Let f prime equal 0. Okay, so let's go ahead and solve for this. So you may already see it. There you go. Good job. So 1 works, right?
0 at 1.
Yeah.
Right. If you can't see it, go ahead and do it algebraically, where you could probably say,
How
okay,
would you do that?
here maybe crisscross,
Yeah.
right? Cross multiplication. So if I subtract 1 over x on each side, so negative 1 over x is equal to negative 1 over x squared. And I'm running a room here, so I'm going to draw an arrow. So if I cross multiply, negative x squared should be equal to negative x. And then now at this point, you should see where you have the only ones that work.
But x does not exist at x equals 0, so that's another.
So you could say here, and then definitely check it though, because we're manipulating algebraically, definitely check it. So then I say, okay, x squared equals x. Now you can even bring over the x and do the quadratic or factor if you can, which you would be able to factor. If you went even further, you'd have what? X squared minus x equals 0. If you factor this, I'm sorry I'm working left to right, I don't recommend doing that, but you get to here, right? So x equals 1. Now x equals 0, that's the one that makes it undefined. Okay, just be careful. Let's plug in back into what makes sense here. So 0 and 1, and then the endpoints. Mm-hmm.